Awesome. So firstly, thank you everyone for being here. I know it's post-lunch, everyone's a little bit sleepy, so we're going to try and make it fun and quick. Yeah. And welcome to our talk, Elevating Red Team Payload. So we have divided this talk into 4 parts. We're going to do a quick round of introduction, and then we're going to start talking about why this talk. So how did the idea came about? What was the intention of it? And then Victor is actually going to walk us through the actual research work that we have done. And then finally, we'll have a look at the outcome and, any sort of learning we had, any future ideas, and so on. So I think I know of quite a few people in the room, but for those who don't know me, hi, I'm Dhruv Bisani. I currently head the adversarial attack simulation team at Starling Bank. Been in this space for 8-10 years. Previously, I was a head of red team at a company called Resilient, which is a consulting company. And my last couple year focus has been delivering red team, developing payloads, and looking after the team really. Have some experience in CBEST, TBEST, regulated testing, and a few different sectors. Last year, I've had a pleasure to speak at a few different conferences as well. And that's me.
Hi everyone, my name is Victor van der Helm. I'm a senior red team operator at Starling Bank. So I have a keen interest for malware development, and I come from a pen testing background. Lately, I've been focusing on researching cloud technologies, working with infrastructure as code, and doing macOS research.
Thank you, Victor. Actually, you can do this. It's too hard to have more. All right. Before we start, a quick disclaimer. So we are not here to discuss anything groundbreaking. We're just going to talk about how some of the ideas that already exist in the industry has helped us to develop something that help us become a better red teamers. We are not expert. We are just here to share our experience. So if you do have any idea, suggestion, or even a correction, feel free to talk to us after the presentation. More than happy to discuss this. And lastly, the aim of the talk is not to give you something that can defeat every toolkit out there or every security toolkit out there, but rather something that can help you elevate your payload creation process. However, I do hope you enjoy and learn something, and something that helps you, implement or better your own processes as well. One last disclaimer, while we both present and represent Starling Bank, there's nothing in this talk that actually relates to Starling Bank itself. So yeah, there's no similarities between what we talk and the bank itself. Cool. So why this talk? I think everyone here who has done red team for a while has seen this problem, that us as a red teamers spend a lot of time writing payloads, debugging it, making sure it works. Once you have the base technique that works, then you go into OPSEC modification, you make sure you add encryption, garbage code, X, Y, and Z, make sure that works. Then you perform OPSEC check, so you make sure your payload is not disclosing anything, not leaking information that is not supposed to. And then finally, you have something that works, right? A lot of this is manual work as well. However, all of this kind of goes to waste when your payload is actually detected. Now, this can happen at any time of the project cycle. So it can happen even before your project starts, it can happen during the project, or it can happen post-project, especially when the blue team takes the payload, submits on different forum, gives it to CrowdStrike, Falcon, they rip it apart, and so on and so forth, right? So we have seen this problem quite a lot. Now, this is what our payload dev cycle looked. Can I have the pointer? Thank you. This is what our payload dev cycle looked like. So usually you would have a technique that you want to implement. So you write a base code for it, and then you make sure the base code actually works. So you test it, you debug it, you compile the binary a few times, make sure everything works. When you have nailed it down, then you go into OPSEC modification. So you'll add encryption, garbage code, evasion technique, so on and so forth. Retest it, debug it, make sure everything else works. And then you finally get into OPSEC check. So you make sure it's good to use, and then you finally have a binary that can work. A lot of this is manual and so on, right? Oh, sorry.
This is my cue. So some of you might be wondering what the differences are between OPSEC modification and OPSEC check. So let's start by just talking about OPSEC. So that just means operationally secure. So the difference between the two is that OPSEC modifications are trying to be operationally secure with your payload. So, using good techniques, whereas the OPSEC checks are more like a sanity check on your final deliverable that you're going to be using within the environment, maybe like a client environment.
Cool. Thank you. Sorry, I had to add this because he forgot this every time we did a trial run. So this is the only way to make him remember this. But what happens when your actual payload gets burned, as we said, it can happen any time of your project, right? It essentially means now you need to redo all of this work to some extent. So you may need to, you can still potentially use your technique, but you may need to update the code. Now that you have updated the code, you need to make sure it works. Redo your modification. It might be quite simple as like changing the encryption key, updating the garbage code, nothing too complex, but you still need to redo it, recompile your payload, make sure this all works, and so on and so forth. And your payload can get burned for several reasons, right? There could be static analysis, probably the most common one. Then you have dynamic analysis, which is annoying, but it can happen. It could be because you did something wrong as a red teamer, so I don't know, you dumped Mimikatz on the disk or something like that. Or it could be because the blue team did something nice and correct, right? Which is rare, but does happen from time to time as well. Now the last two is probably okay. It happens with everyone. There's nothing much we can do about it in terms of automation and helping you be better. But the first two, the static analysis and some basic dynamic analysis. Now, there are different levels of dynamic analysis, and if it's, you get burned because of some complex reason, that's fine. But there are some, AV evasion, and if you get burned because your payload wasn't able to bypass an AV sandbox, then it's kind of annoying. So this kind of got us thinking, actually, and all of this results in more manual work and time pressure, right? So especially when it happens during an assessment, or you're in a consulting company and you're back-to-back project and your payload is burned, it creates an immense amount of time pressure to do all of this again and make sure you have a binary that works. This kind of got us thinking, can we do this better? Can we reliably defeat static analysis? So at least we don't want to get burned by something really stupid. So can we make sure that we consistently defeat static analysis? Probably create more opportunity to defeat dynamic analysis as well. So we're looking at some basic dynamic analysis, not really complex ones. But in essence, can we aid overall payload OPSEC to improve the payload creation efficiency? So can we make this as a part of payload creation cycle to make sure we can do all of these stuff, right? And the answer was yes. We were able to achieve some element of this in GitHub Actions. So what we're actually trying to achieve is we're trying to increase the usability of dynamic analysis evasion technique by consistently defeating static analysis. So what I mean by that is, if I go back for a second, this technique is probably going to get analyzed every time your payload gets burned. So we were trying to make sure is that our payload is not getting burned because of stupid mistake, which essentially means that our dynamic analysis technique lives a little bit longer than it would have otherwise. And we want to try and do it in a little bit more effective way. So, a little bit more automated, a little bit more quicker. A quick side too. So what is GitHub Action? I'm sure everyone here knows this already. It's a CI/CD platform that allows you to automate workflows. So you can automate building, testing, and debugging your code as well. As the name suggests, it integrates with GitHub. And the aim is really, automating routine tasks. It's probably worth mentioning this concept can be applied to any CI/CD platform. GitHub Action is what we use as a team. We're just more comfortable with. We had something similar in my previous place. We used to use Azure Pipeline, so pretty similar concept. So any one of them really work, so on. Let's take a quick side step before we get back into the research. So when we talk about static analysis, dynamic analysis, what are we actually referring to? Okay. It oddly looks different on screen versus what it looks here, but that's fine. So there's a lot of things that happen when you talk about static analysis. These are just 8 of some of the common things that we're looking at. Making sure it's not getting detected because it has similar signature or it has a bad entropy, clear text string and shellcode. Making sure it doesn't have anything suspicious in the binary itself. And of course, it's not limited to these 8 things, but this is kind of the things that we looked at really. Now, dynamic analysis can be of various types as well. We divide into 3 parts, but it could be more than that. So when we say emulation, that's looking at when your binary is actually run in a sandbox environment. Action is what you're trying to perform with that binary itself. So the base technique that you're trying to implement. And then behavior is what you do post implementation of your technique, or what the user is actually doing, or what are you as a red team operator are doing from that C2 connection that you've achieved. And then lastly, we're also trying to defeat logistical challenge. So we're trying to defeat the fact that we have limited time, which means doing this creates a lot of pressure on us. We're trying to make sure there's no, there's less effort, and we want to do it we want to overall increase the shelf life of our payloads as well. So for this talk, we're going to focus on everything that's been marked on green, really. So we're going to look at how we can consistently defeat static analysis. maybe a little bit look at the emulation as well, and all the logistics challenge as well. And we want to do it effectively. That's the key part of this process. Like, we want to make it effective. We want to make it, easier for we want to make our life easier as red teamers. So when we go back to the research, so as we spoke, this was what our sort of payload dev cycle looked like when we started this research. And somewhere midway, it kind of became this. So we started automating some of the routine tasks. So, making sure adding the modifications, so changing the encryption key or adding garbage code evasion, compiling of the payload, and doing some basic OPSEC checks. So we automated this. Now you can potentially also automate the debug and testing. We didn't do this for our pipeline, I guess. We still haven't implemented this actually, but we can potentially do this, if you had to. And this is what the end looks like for us now. So what we were able to do is add, instead of having one technique for everything, we were able to add more options, which allows you to create more variation in your payload every time your pipeline runs. So instead of having one way to encrypt your shell code, we're able to implement 3 different things, and each one of them has a bit of variety to itself as well. So your natural language could be anything from Hindi, Urdu, Spanish, English. You can choose it, and you don't have to worry about doing it manually. You probably can define it in your pipeline. It will do it automatically. XOR or your string encryption can be various one. We have implemented 2. You can have different garbage code functions and so on and so forth. You compile it through different variations, and Victor's going to walk through why we have so many different options. But the idea is, instead of having one way of doing it, we have multiple options. It's all automated, so you can create different types of payload, and you don't have to spend manual time to change your code as well. I think it's probably safe to say, and I hope Victor doesn't mind me saying this is not the end of the pipeline. This is where we have got so far. There's definitely a lot more work to be done. We can probably automate debug and testing as well. Probably can have some element of AI if you want to change garbage code. I know there's no talk complete without talking about AI, so we could do that potentially, and so on. Now that's a lot to cover in next hour. So we're going to focus on everything that's marked in yellow. The main reason being, I think we think that's probably the most interesting part of the pipeline. If there's any other part that you're interested in and you want to know more about, feel free to talk to us afterwards. And yeah, so there you go.
Thank you, Dhruv. Okay, so I'd like to focus more on the pipeline itself and the individual components of the pipeline. So the idea with the pipeline was to create some sort of randomization where possible and swap out components to ultimately have a binary that performs the same sort of actions but looks different on disk once it's been compiled. So let's start by revisiting GitHub Actions in a bit more detail. So here on the screen, you can see a little screenshot of what it could look like. So GitHub Actions are represented in the format of workflow files, which are in YAML. So each workflow file has a set of jobs that are kind of chronological. So they kind of determine the flow of the automation. Each job can have a number of steps which can perform smaller kind of instructions to complete the overall job, and these jobs can be conditional. Furthermore, the workflow files kind of have a trigger, so the trigger will determine when the automation will run. So here it's on line 3, you can see it's set to on push, which means that whenever you push code to the repository, it will run your automated build. Furthermore, like some nice features of GitHub Actions is that you can set a runner environment against every job. So when you have a job like this one, you can specify as to whether it's to run on Ubuntu or perhaps Mac OS or Windows, depending on what kind of what you're doing. You can also import like community jobs. So if anyone released like a public pipeline or some sort of automation, you can kind of pull it into your pipeline and use that. And then another nice few things is that it allows for you to log basically everything that you do within your automation, and it allows you to create artifacts like EXEs or DLLs, etc. So here on the right side, you can see what our pipeline actually looks like. So that's all the files we have. It's really not too many. And they can, you can kind of sum this up as being a combination of YAML, C++, Python, and Bash code. So the YAML, as we mentioned earlier, is to kind of define the overall logic of your pipeline and what the pipeline is going to do. In our case, we opted for C++ code for our malware. That's something I was most comfortable with, and that's therefore what I wanted to use. We used Python, specifically a Python module, to kind of manage the C++ code that we have and kind of manipulate the malware within the pipeline. And then lastly, we use Bash to do any kind of high-level file operations. So renaming files, copying files, maybe running some kind of tool. So obviously, with all this stuff, you also want to, have any kind of relevant resources that you may need for whatever you're trying to achieve. So you might want to have like a shellcode file that you can use within your pipeline, or perhaps you might want to use some sort of precompiled tools like SigThief or ThreadCheck, or something like that. And yeah, it's important to note that you can ultimately represent this pipeline in any language that you want or are comfortable using. The only static language here is YAML, which you'll have to use for GitHub Actions. Nice. So let's talk about templates. So you need some sort of template that you can use within your pipeline in order to get something useful out of the automation process. So there's a few important things to consider here. You need to have a good base to work from. Your template would ideally contain your core EDR evasion features, whatever that may be, and it has to kind of allow for you to modify the base template of your malware some way. So we're kind of we're trying to achieve randomization, so we want it to be kind of compatible with this aspect. So just a bit more on good design. So you'll get the most out of this kind of pipeline if your template kind of implements some good MolDev practices. So or rather techniques. So these could be things like obfuscation of strings and shellcode. Things like dynamic function resolving. Maybe with get proc address and get module handle, or maybe some assembly. Some sort of core EDR evasion, sandbox evasion, and just generally some good OPSEC. So each one of these kind of techniques has multiple implementations. So they're all, within a red team engagement, or perhaps across red teaming engagements, you'll be changing these things. So let's say you have a payload with XOR encryption, maybe it gets burnt, and you'll try AES encryption, for example. It's a terrible example, but you might do something like that. You'll swap out a technique. So these are all great kind of candidates for being randomized within the pipeline. So let's look at some things that you should probably avoid. So things like non-obfuscated shellcode, which is statically defined in your template. That's just a bad idea. It's likely to be super signatured and probably unlikely to execute. In fact, yeah, you should just completely avoid using static shellcode. I'll get it soon enough. Yes, so things like direct function calls of suspicious Windows API functions. So things like open process, virtual alloc, virtual protect, create remote thread, classic example of remote process injection. You want to avoid that, or at least calling them directly, because they'll show up in your binaries import address table, and it's just a massive red flag. I got it right. And lastly, things like mimicat strings or any kind of string that contains sensitive content, or anything that that would be suspicious in any way. Just avoid it.
So I think one thing I want to add is, the point of this talk is not a malware dev 101. So this is not everything you should or shouldn't do, but the conceptual idea is, just because you have a pipeline doesn't mean you don't follow the basic security best practice when you're doing your malware dev. It all depends on how good your base template is, and you're trying to improve it from the pipeline itself.
So yeah, let's look at maybe a template that might be a bit better. So a template that's better or good would have things like obfuscated shellcode and strings. So you could potentially have a decryption key, which is hosted within a domain DNS record. So you can have a CNAME record that contains your decryption key, which you could fetch within your malware. It allows you to kind of control when your malware runs and how far someone can go debugging or reversing your program once it's been burnt. It's also good because you don't have a static key in your malware. So you could also consider something like using indirect syscalls for your EDR evasion logic. So this would be a good candidate for any userland hooking EDR. It obviously may not work so well against ETWTI kind of based EDRs. You'd have some logic to retrieve your hooked syscalls, and you might consider using something like local process injection rather than remote process injection because it's got less IOCs. You might have some sort of sandbox evasion, some random code, etc., or even assembly code. So again, these all kind of provide opportunities for us to randomize these bits. So here we have an example of our template, C++ template here, and you can see it's got some sort of placeholders in the red boxes. And what we can do is we can create a Python function that you might be able to see on the left, which will look for a specific placeholder in our C++ template and then replace it with whatever code we want. So we could create some blocks of C++ code within our Python module, which we can then inject within our C++ template wherever we choose. So you can do this for C++, you can do this for assembly, you can do it for any language that you want to work with, C#, Rust, Go. Yeah, it just fits kind of most things. So this is an example of how you could run this injection logic. So on the left side, you can see an example of us injecting garbage code into our template. You'll see the placeholder garbage_txt. And then on the right side, you can see a snippet of our GitHub Actions workflow file where we call our Python module with some arguments. Okay, let's dive a bit more into the individual OPSEC modifications that we perform in our pipeline. Sorry. So obfuscations. So again, the aim here is to kind of have a variety of obfuscation methods, whether it's encryption or encoding, that we can use randomly, we can select from randomly within our pipeline build to create a somewhat unique binary at the end of the process. So, we've got a number of encryption and encoding techniques for both shellcode and strings, things like XOR, ROT13. We have like a custom assembly function, which will do some encoding. And we also use something called lookup tables. So lookup tables, I guess, is something more like encoding, and we thought it was quite interesting, so we'll talk to you about it. So if we consider something like emoji lookup tables, we can basically take our shellcode, and specifically every hexadecimal byte within our shellcode, and map it towards an emoji, which will act as like a legend or a key, and that could look something like this. So we can have here, it looks quite nice, and on the top you can see we have our like our legend, and at the bottom you can see we have our shellcode, which is represented as emojis. So what we can do is we can run a couple loops, and we can derive the original shellcode from these emojis by looking, cross-referencing them. And this is quite good because this results in low entropy if you were to, define it within your malware directly, and it looks cool. So again, same as with obfuscation, with garbage code, we're trying to grab some legitimate code and randomly inject it into our binary. So when I say randomly inject, we're trying to end up with different bits of legitimate code across pipeline builds of our malware. So here we just for the sake of demonstration, we've got 4 mathematical functions, which like quicksort or Fibonacci, and we will just place them within our template and then call them, and it kind of helps create more randomization across your binaries. So in the screenshot, you can see a picture of us defining some C++ code in Python, which will then inject within our template with the methods described before. So let's talk about the kind of modifications we could do relating to evasion. So if we consider sandbox evasion, the aim of it is basically to allow your malware to execute from a sandbox environment or a detonation chamber. So you want to exit out of your program if you identify such an environment. The idea being that you could get to protect your sort of malicious logic from being detected or analyzed. So what you'll do is you'll run some checks and try to break out of the environment as soon as possible. Oops. So we implemented a couple techniques that we can select from within our pipeline. So the first option is something like hardware checks, where we check the CPU cores, RAM, and screen resolution of whatever host is executing our payload. And basically, the more scarce the resources, the more likely it's to be something like a virtual machine or a sandbox of some kind. The other kind of checks we do is we check for mouse movement and for recent files. And that could, from that we can infer whether or not there's a user behind the host executing our malware. Here we have some examples of our code. Obviously, it could be better. If we had more time, we would customly resolve these functions, would dynamically resolve these functions. Okay. So this is something that we called assembly fluffing. It's probably not called assembly fluffing. It's a random term that we gave it. But so the idea here is we're using indirect syscalls within our template. And here we have an assembly function, which is the indirect syscall. This indirect syscall function will be used across multiple builds of our malware. So what we want to do is kind of avoid it from being a signature that is, as it's like a core feature of our dynamic analysis evasion. So what we can do is kind of scramble its representation on disk. So on the left, you can see that we've defined some assembly instructions, and these would be no operation instructions. And basically what we're going to try and do is randomly place these assembly instructions within our indirect syscall function in such a way that it just adds extra instructions and changes its representation of the overall function. Ultimately it won't change the outcome of the indirect syscall function. So on the right, you can see some Python, which will just loop through the original code and then place some of these no-op instructions within that function. And that'll look like this. So everything that's indented is the core indirect syscall function instructions, and then everything that's been placed at the margin is the no-op instructions that basically doesn't do anything. It just adds some extra fluff. Okay, so let's talk about compilation. So within our pipeline, we implemented several types of compilations, and the idea of that was to kind of end up with different types of binaries or EXEs at the end of the process that we can then compare and analyze and determine, which ones would be most suitable moving forward. So each compiler is kind of implemented differently. They all have different ways of optimizing code, and they all, place different kinds of functions by default within the IAT of the binary, especially if you're linking to the C runtime. So furthermore, the outputted binaries based on the compiler will have different sizes, different entropies, different strings, etc. So for our pipeline, we've used the cl.exe Visual Studio compiler, LLVM for Windows, MinGW for Windows, and obfuscated LLVM. So you're probably wondering what obfuscated LLVM is, and some of you might already know what it is. So it's basically a custom version of the LLVM compiler. And the LLVM in itself is almost like a back-end module of many compilers today. And what's so good about it is that it turns C++ code or C code or any other compatible language into an intermediate representation language, which can then be modified by something known as passes. So the obfuscated LLVM compiler has some predefined passes, which will look to modify the code in such a way that the outcome isn't changed, but it'll perform some sort of obfuscation. So the kind of obfuscation that occurs is it can change the control flow of the program. It could implement some fake loops. It could substitute instructions within the program or perform some sort of string encryption. And ultimately, you can expand on it as much as you want, and you can customize this whole process. You have a nice screenshot here showing you how it works. So the pros of this is it has a lot of potential. It's actually been adopted by Cobalt Strike's Mutator kit recently too. The cons is that it's not straightforward to use, build, or customize. Nice. So what we did is we built the obfuscated LLVM compiler within a Docker container, which we then download and use within our pipeline whenever we run the pipeline. So within the screenshot, you can see us using the GitHub Actions workflow file to randomize basically some switches that are passed to the obfuscated LLVM compiler. And then just below that, you can see us passing these environment variables to a Docker container where we then perform the obfuscated LLVM compiler compilation, sorry. So the idea is that we randomize each one of these switches, the number of fake loops or the number of instructions which are substituted is different across different builds.
Thank you, Victor. So let's look at what the build process actually looks like after we implemented all of these techniques. So this is what the pipeline looks like, as we said, right? Now let's, as Victor mentioned initially, that for us the pipeline builds every time we push a new code to the Git repo. So let's assume that we are on a project, we want to build a pipeline, so we did a push, and then we have already implemented the technique and the code template. For the sake of this, let's assume the testing and debugging is already done. As we said, that is something we do manually. So we manually make sure the base technique actually works. But what happens post that is the pipeline goes into OPSEC modification phase, where we'll go through each one of these sections and choose one thing randomly. So we'll go through encryption, take the shellcode that we have, and it will choose a technique randomly, and it will randomize things where possible. So I know Victor spoke about lookup table. So it's going to look different every time in every binary. So even if you have two binary shellcode encrypted using emojis, if Blue Team is trying to decrypt that, it's going to be two different keys for every time. So, it's different for every build. Same for strings and, encoding as well, or encryption, XOR, it will change the key every build as well. Then it goes garbage code and it takes one of the 4 functions we have. Now, I think there can be a little bit more work done here, so you can make it more dynamic instead of having 4 set of function, or you can probably get, it to pick functions from MSDN websites to make it more legit and things like that. It will go into the evasion phase where we'll choose one of the technique and again randomize where possible. So it could change the sleep time, or if it goes recent file, it can change the parameters and number of recent file we're looking at, and so on. And then for us, it compiles in every one of the compiler now. One very interesting thing about GitHub Action is it's almost like building your payload in a sandbox, because when you actually run the GitHub pipeline, it goes and runs in a virtual environment that you physically cannot see. You can see the logs of it, but you cannot see that. So one thing to be really careful on, and I'm not pointing fingers on anyone, but when you try to do this and you're trying to debug if your code is working or not, you may end up rebuilding pipeline every time. But your GitHub tier gives you a free limited amount of time, right? And when you build 24 binaries on every build, it can cost you a lot of money. So just be careful of that, or you can run out of all the time that you have and then you have to pay more. So just to be a little bit careful. But for us, every build will give you 24 different binaries, which is different combination of all the features that we have. Now I'm sure everyone's thinking, how do we know which binary to use? Which is where the OPSEC check will really come in. So now, and Victor will walk us through in detail, but we'll perform OPSEC check on each one of these and see which one is the best suited for the environment that we are on.
Okay, so let's move to OPSEC checks. And so this is like the least sexy part of the pipeline. but it kind of meets all the administrative needs, which Dhruv will get into later. So one of the checks we do is we use Rastermouse's thread check to basically scan our binaries to make sure there's no, it's not, our binaries aren't signatured before we even use them. So this is a nice sort of sanity check to perform. We also look for kind of keywords within our binaries. So, what you could do if you're a consultancy is you could look for client names within your binaries to make sure that they're not being leaked to other clients, or you could look for, I don't know, any other sensitive keywords or strings that you may have. You could scan your binaries with YaraForge, which is basically a Yara rule set, which is publicly maintained. You can look for bad bytes similar to ThreadCheck. You can look at your binaries entropy levels to kind of determine whether or not it'd be suspicious and whether you should use them. You can look at the imports and exports of your binary, and if you wanted to, you could grab the binary file hashes and kind of look them up and see if they were malicious before using.
Yeah. I know Victor said this is the least sexy part of the pipeline. I do agree to that, but if we have any red team managers, senior people who have, juniors working with them, I think this is probably the most important part of the pipeline, because it allows you to make sure that you have that consistency every time a payload has been built. So you make sure that, if someone less experienced, or even, us as seniors, when we try to do this under time pressure, can make that error, is just having that peace of mind that everything that we use is being checked once before it goes to the client. It gives you a little bit of reassurance that, it's not going to get detected because something of stupid.
So here's just an example of how we use ThreadCheck within our pipeline. So we basically compile all our binaries and then run ThreadCheck against it. But yeah, this slide is mostly just credit to Rastermouse. So when you perform your builds, it's nice to have some sort of report as to what happened and what occurred within the build process. So on the right here, on the left, you can see a big list of all the things that were compiled, and you can see, whether they passed or failed the different OPSEC checks. So you can see here most of them passed the thread check and YaraForge checks. You can see things like the file hashes there and the entropy levels. You can also kind of see on the top right here the kind of method, the random components that were selected. So as in the type of shellcode encryption, we see here it's random lang. It's basically all the shellcode was encrypted in some sort of random language. It could be, Hindi, Chinese, whatever. And then we know what kind of signature was used to perform the fake signaturing, fake signing of the binary, and what kind of encryption was used for encrypting strings, and then lastly, what sandbox evasion technique was chosen for this particular build. So we've talked to you about, our amazing pipeline and all the hard work we put in and how cool it is, but, you're probably interested in the actual results. So here we've basically run our pipeline 3 times. So these are, and then from each pipeline build, we've selected one binary. So the idea is that every pipeline build would have selected a different set of techniques that would have been randomized. And yeah, so you have 3 different binaries. So the first one was compiled with LLVM for Windows, the second one with MinGW for Windows, and the last one with our obfuscate LLVM compiler. The second and third both used XOR for the shellcode encoding, whereas the first was Urdu lookup tables. They all had the same sort of string encryption method, and again, the first and third had the same sandbox evasion technique, which was hardware checks, and then the second one had a mouse and recent files check. Lastly, the second binary was also fake signed with the MSI Afterburner setup tool, and the last binary, sample 3, was also padded with some random junk to make it a lot larger and hopefully harder to analyze. So we'll just run through some kind of characteristics of these binaries. We put them all in PE Studio to kind of see what the import tables look like. A number of functions were kind of identified as being malicious. However, the one that kind of really stands out is in the second binary, and that has a virtual protect function. There's a table from that Mezzo released on Twitter just a week ago, and I stole his screenshot, his image, and basically used it here. But you can see that the percentage of occurrences of these malicious functions and virtual protectors in that list. We also wanted to show you the kind of control flow graphs of each binary. So you can see here the first and second binary are very similar in the kind of conditions and jumps and loops within the binaries. So the flow is all very similar. Whereas the obfuscated LLVM compiler, which we were talking about earlier, that really completely scrambled and mangled the binary. So the flow is completely different. There's a lot more checks and loops and all sorts of things in there. So it's a lot harder to kind of reverse and understand.
One thing I would actually like to add is one thing that I find really interesting here is that, and Victor, correct me if I'm wrong, but the virtual protect function in the sample2 is not actually in our base code itself. So it's something that was actually added by the compiler, which, I would have actually never really paid attention to unless I was actually comparing a few different options. So I think that was a really cool thing that we found out. All right, let's look at the first, the fact that, the functions and the flow. How many of you think that sample 3 is actually the best binary to use in an engagement? Can I get a raise of hand if anyone thinks sample 3 is the best one? No? Sample 2? Sample 1? Ah, cool. Let's see.
So the answer was actually sample 2, which is odd because it had the virtual protect function within its import table.
Sorry, can I add? Andy, why did you think it was sample 2 and not sample 3?
Which sample?
Sorry?
The more complicated you make a binary, the more likely to get. Sorry, I just stole your thunder.
No, that's all right. And obviously we see that the obfuscated LLVM one has the most detections out of the 3. But overall, I think all of them are quite low. So what can we kind of infer from this? Well, more complex isn't necessarily better. So it might be about finding, you might have to kind of find the sweet spot between doing too much and doing too little. And it could also, it might be vendor specific as to what binary you should choose and things like that.
All right, so let's look at the final outcomes that we have. So at the start of the presentation, we had 4 questions that we asked to ourselves when we started doing this research. Can we do this better? So can we reliably defeat static analysis? I think we were quite happy with the answer. I think we can do that definitely with continuous R&D and the pipeline, making sure there's checks in place so we don't do anything stupid. Which essentially does create some opportunity to defeat and focus dynamic analysis. Of course, the focus is not to always defeat it, but it can help you a little bit better. The next does it overall aids the payload OPSEC? The answer is definitely yes, because you're doing a bunch of checks. You're adding randomization. Every binary is different. I think it's quite fun to throw blue team away when you have a bit of Chinese characters in your payload or Russian language in your payload. So that could be quite fun as well. And then overall, does it improve the efficiency? Definitely. Something that used to take us a day or 2 to update the code, change stuff. Now just takes us a couple minutes to do it. It does cost me a lot more money when I let this guy develop stuff, but it does help for sure. Yeah, and in conclusion, the idea really here is the scalability and banking on capability. So the more randomization you can add, the better it can become. And I think the main thing is also it can be tailored. So of course we do it for our C2 and stuff, but you can implement the same concept for any kind of payloads that you want to develop really.
So given more time, what would we kind of do as improvements? So we might consider randomly choosing EDR evasion techniques that we can inject within our template. So you could, be banking up these evasion techniques in-house and then randomly select one within your template. Would probably consider improving the obfuscated LLVM compiler and creating our own kind of obfuscation passes rather than using something public from the internet. Would probably try and figure out more about the dynamic analysis, or rather the actions that relate to our binaries by, implementing some sort of restricted EDR or other form of dynamic analysis within our pipeline. And lastly, we'd look at handling different types of output files like DLLs or macros or whatever.
I think that's pretty much it. Thank you, everyone. That was a nice All right, we got a couple minutes if anyone has any question. Yeah, go for it.
Just regarding the antivirus results, I'm just curious what engines actually detected the
Well, funnily, I think the one that was constant across all three, was some Chinese AV called BP or something. I can't remember. But the none of the really big ones were consistently defeating all three. It was a different kind of reputable AV that was detecting each one of the three.
No, so the only way to do it, actually run it on GitHub. I think you can have GitHub offline runners, but that still costs you, which is what I was saying. It does cost us a bunch of money, and trying to explain that the business can be tricky, but it just pays off definitely. Anyone else? No, I think that's okay. Yeah. Oh, you.
I was just curious about, how you had the trees that showed how the binaries were created. Is that something that you wrote custom, or is that just a piece of software that's not ready?
Oh no, quite a few of the decompilers will have a graph view. So this one was IDA free, but I think x64 DBG would have it too.
Cool.
A new template?
Component.
Well, if you use ChatGPT, you can probably do it really fast. I think normally you want to test it, make sure it's robust. So I tested all the individual blocks of code that we injected into the template. You want to make sure it actually works properly and there's no bugs in it. And then once you're really happy with it, then you'd add it to your sort of database of code.
Are you guys only doing Windows skills? Because this is very Windows-centric. Are you doing it for Linux and Mac OS as well?
I think the intention is there to do with macOS as well. But of course, I think it was easiest to start with Windows and kind of develop from there. So at the moment, it's only Windows, yeah. Anyone else? No? All right, cool. Thank you, everyone.
Thank you.